Hey, hello there, and welcome back for more late night coding. So, yeah, Advent of Code day 24. We are back with this, and let me tell you, first of all, I got the answer for part 4. Part 2. It was quite a grueling experience, it was also quite fun, I could say, in the math kind of way. I've tried a bunch of different things. I wasn't recording any video with this because I was just trying to understand maths and trying things out, so I didn't think that it wasn't coding at all. But in the end, the solution that I got it using a symbolic algebra package from Python called SymPy, and I've done this on a notebook on one of these Google Colab thing that are quite amazing because you can use everything for free. I could have also done this locally on my machine, but it's nice to have something to try things out and prototype something and get a solution. But before jumping to that, let me tell you a little bit about what the hell was it that I did. Sorry, I was looking for my cell phone, which is right beside me, and I was not seeing it. I just want to put a stopwatch running. Okay, so this problem, where do I start? Yeah, so what we are doing here for part 2, just to revisit this, we have a bunch of hailstones that are falling, and we are given the hailstones' initial positions and velocities. And on part 1, we just calculated some intersections in 2D for these lines. It's not important because it's not very relevant for part 2. There is some hints though in part 1, but part 2 makes us compute something completely different. Basically, it tells us that we can throw a rock, also like the rock works from in a similar way to these hailstones, like it has an initial position and a velocity, a constant velocity in 3D. And if we carefully choose an initial position and a velocity, we can hit every hailstone on their path, and we are going to hit them like at integer positions. So you can think of all of these as integers. No need to even worry about decimal numbers or anything. But the thing is, how the hell do you calculate this position and velocity for the rock that you want to throw? And well, the sample solution has 5 hailstones, but the actual input has like 300 of them. But you can think that the title of this puzzle is never tell me the odds. Like the odds of all the hailstones flying around such that you can throw a rock and hit every one of them, like a rock in a straight line, and you can hit all of their trajectories just at the time that they are passing through that line the odds are astronomically low. So of course this input is crafted in a way that this is possible, and yeah, we have to find basically a line. What we are looking for is a line that intersects with all of the lines that define each hailstone is basically a line. Given a position and direction, you get a line, and you want to find a line that intersects with all of those 300 lines. Basically, that's the problem for part 2. And I was thinking about this, and I wanted to see if I could solve this algebraically in some way, and that didn't lead anywhere. I started doing this with pen and paper, and I don't know if you can see, I have a page, not a full page, but a page with long equations that I was trying to work out, and this didn't went anywhere because the equations were ballooning ballooning in size. Let me tell you basically what was my idea. We have these notes here. these are the nodes for part 1, but I remember that I have a couple of like equations for lines written down here. So let's get rid of everything else because that was for part 1. So basically we have a bunch of lines, and we have 300 of them on the real input, but on the sample we have 5. So that's already a hint. Like with 5 lines, it seems to be possible to find this, and actually with less lines than that, it's possible. I think with 4, it's like I used 4 on the actual solution. And by the way, I got the solution in this session. The only thing that I want to is like get this into maybe a better shape and have something to commit to the repo, but yeah, the solution is already there. So okay, let me tell you about the first thing that I try to explore. Like, these are basically the parametric equations that define 2 lines. You can say that the line is every point xy that is itself like an initial point. I call it x1 and y1. This would be like the initial position of a hailstone, for example, plus t, this is a scalar variable, times a velocity vector. So this would be the velocity of a hailstone. This actually, I wrote this in 2D, but this would be in 3D actually for part 2. But we can write this, instead of writing these vectors like this, we could say, okay, this would be the initial position for the, P represents a vector here. And this would be P1 and P2, like the initial positions of these hailstones. And let's write it, write the, how do you say, the multiplication explicitly here. A t variable times a direction, the direction of the first hailstone, and then, I don't know why I'm using t here, a u variable, like another variable, times the direction of the second hailstone. So this would define like the 2 lines of 2 different hailstones, and we could actually write it like this, maybe. Yeah, like all the, like L1 would be the line that represents a hailstone, and it will represent all the points. So, and these are 2 like constants, and these are the only variables that that you like go along. And like my idea was, okay, we can think about the solution line, let's call it S, which will also be a line, as a line that whose points, like you can define this line by given 2 points, and it will be the points that go through line 1 and the points that go through line 2. But you can think about this in 3D, like imagine any line and any other line that is not necessarily parallel or doesn't even intersect, like these are 2 different hailstones, and what are all the lines that intersect those 2? Like if you kind of visualize this, I don't know if I have some sticks or something, maybe with Sharpies. You have like two different lines, and if you think in 3D, like how many, there are infinite lines basically that can connect every point on this line and every point on this line. If you actually take a point on the green Sharpie, these are not Sharpies, but marker line, and you think about a given point here, like you still have infinite lines that go through that point and go to the red marker, right? And they form like kind of a, would you say, like a cone thing, but not in 3D, like they are like in a plane, right? Because this is a line and a given point, a line and a point forms a plane, and there are infinite lines on that plane that crosses through that point and through that line. And then you can choose any other point. So it's like you have 2 different variables. So that forms like a sort of volume. You can try to imagine that volume in 3D. That are all the lines that go through this line and this line. So that's a weird shape, for instance. But we can think about this. Like we can express like S as any point that goes through line 1. So let's call this thing L1 because that's are all the points that go through line 1. And let's actually call these parameters some like T1 and T2 just to represent like two different scalar values, just to be generic and use the same indices for this and this. So the solution line would be this plus another t variable, like another scalar variable, but let's call this just t because it's part of the solution, plus times the direction that connects L1 and L2, and to get that you can just do L2 minus L1. This would give you a vector. This would represent any possible vector that connects L2 and L1. So this would be the direction, and this is basically the general, like if you substitute this with like I don't know A and B, this is the general equation for a line that goes through A and B. This is the equation. And here I'm writing the same, but instead of just any 2 points A and B, these are points in line 1 and line 2. Okay, so you can write this, and you can think that this has, apart from this T that would represent how far along you are in the solution line. So if you have this, again, these two lines, and the solution line is something that crosses these two, like in any direction, the T would be the how far along you are in that line, and then each of these points itself will have another T, like would represent like how far along you are on those lines. So this thing actually is not unique, of course, because all the points on line 1 it's like a cross product of all the possible points. But we can have more lines. We can have a third line, for instance, and well, I don't know why I did that so manually. But then you can have another equation for the solution line, like the same line. You can say, okay, it also has to go through line 1 and line 3 because it goes through all the hailstone lines. And this is basically another way to express S, because it also has to go. And you can imagine like that weird volume of possible solutions. If you have yet another line that this solution line has to go through, that would make like the intersection. I don't know if it's even the intersection of two volumes, but like if you have to find the solutions of these two things at the same time, you're reducing basically the possible solutions. And that was kind of my idea. It's a very like complicated thing, and I thought, okay, like these are the same S, and of course here like L1, like the first point, I'm choosing the same. Oh, by the way, here I should use another T variable for this, like so we are adding more variables to compute. But my idea was, okay, this is the same point, and this is the direction of the line, L2 minus L1, and this is also the direction of the line, like the difference between these two lines that it is intersecting. So this means that the directions has to be equal, right? If it has to be the same line, like it has to, it has a given direction. So L2 minus L1 has to be the same as L3 minus L1. And sorry, not the same exactly, because this is the difference between two vectors, but they have to be parallel vectors. L2 and L1 has to be parallel to L3 and L1. And how do you know if two things are parallel in 3D? Well, that is the cross product. So this is the same as saying that the cross product of this and this has to be 0. And that was basically what I tried to do on pen and paper. The cross product of two of two vectors in 3D is another vector in 3D, and that this basically gives you, this equation here basically gives you three equations. One for the x coordinate, one for the y coordinate, and one for the z coordinate. All of them has to be equal to 0. And I try to follow that, but the cross product just makes a whole mess, and that's what got like the equations getting longer and longer. Like these 4 lines are just for the first coordinate of that cross product, like expanding all the equations of this and not using just p and like vector variables, but actually like single coordinate variables. And it started to be a mess also because this was not just a linear equation. Things start to get like a bit quadratic, because when you do the cross product, you are crossing x and y and x and z and the different coordinates, so it starts to get so messy. So long story short, that was not really a good way to go. But well, this got me thinking, like there must be a simpler way to do this. Spoiler alert, there is. But I was thinking, okay, if I, like, imagine if this thing worked, I would have to probably add a 4th line here and also say, okay, and the difference between, L4 minus L1 would also, give me another equation to solve. And maybe I can then like cross these things, like L2 minus L3 should also be parallel to those, and so that I can get a lot of like cross product equations from those things, and that I think should give me enough equations to solve, because basically I will need to be solving for these t1, t2, t3, so that those are like 3 variables. And then for each of these other scalar variables that you add for, but you only add one, and then you got a cross product that gives you 3 equations. So I think the amount of equations should be enough to solve for those variables. But this seemed like a mess. And my idea was, okay, if I continue with this, at some point I would get like the direction of this of my solution line, and with this direction I can then have I'm not exactly sure how I would get the position, but I guess with one direction, with the direction already you can check for the intersection with other lines. Because imagine again, let's go back to the Sharpies. If I have the solution line somewhere, like I know the direction of that already, then I can get like 2 points on this line and that direction, compute a plane for that, and see where that plane intersects any other line that I want to see, and that those points of intersection will be actual points on the line, so I can get the point on the line. But then I also need, like, for the actual solution of this thing, I need to know the actual t coordinate, because basically this what we need to do is, like, we need to know exactly where the rock needs to start. This is the solution for the sample. It needs to start at these coordinates, so we throw them, and like all of the hailstones are taken at the same snapshot, like at the same time, and our rock also starts at the same time. So basically they are advancing in time at the same time, like in unison, and our rock has to intersect all of them. So even if I got like the once I got like the direction and the position of the rock, or actually the direction and some intersection of the rock, I need to calculate its initial position. And to do that, if you know already the direction and one point that the solution goes through, it shouldn't be too difficult to, like, where it intersects with a hailstone line, and you can know exactly at what time that hailstone will reach that point. So you get the t for the hailstone, like the time for the hailstone that will be at that position, and you also know, okay, the rock has to be at that point at that time, at the same time that the hailstone to intercept it. And then you can do that for another point, like let's say for the red line here. So you compute another time that the hailstone will be at the intersection, and then you have two different times that you know where your rock will be, and you can like make the difference of those times. Like it should be pretty easy from there to get to extrapolate the initial position, basically, of the rock. But that got me thinking, like, I'm not using the position and the time of the hailstones more directly, and that's basically the got my second idea, which was much more simpler, and that's what got my solution. You can think that all of these lines, all of these hailstones, basically are traveling at the same time, so you can use like the same time variable for all of them, and your or our solution line is also a, let's call it R for the rock position, because this is the rock that we are throwing. It's also a rock position, like an initial position, times a plus a t times a velocity. I call it direction, but I think I should have called it velocity, because it's not just a direction. Sounds like a unitary vector, but this is a velocity, like its magnitude is important. Let's call it rock velocity, just to be clear. So rock position and rock velocity, yeah. But they are all going at the same time. So that's something that I was missing, and I can use from the get-go. And if you think about it this way, you can say, okay, this solution intercepts all these other lines. So remember, like these lines represent like xy coordinates, and like we are saying, okay, there is an xy coordinate on the solution that intersects with L1, and we can find it by like equalizing these two things. We can say, okay, the rock position, like the equation for the rock, must be equal to the line 1 position, like at exactly this time, right? Because if we start at the rock position and travel in the rock velocity by this time, this will intercept, by definition, what you are looking for, it will intercept the hailstone, the first hailstone, starting at the first hailstone position and traveling at this velocity at time t. Like that's what we need to find. And this is already one equation, but this is one equation in 3D, so it's like 3 equations. So let's think about like, and we can do this for L2 and L3 and L4 and how many lines we need, basically. But let's think about what we are trying to solve here. We're trying to get the initial rock position, which are 3 coordinates, so those are 3 variables, and the initial, the constant rock velocity, which is also 3 other variables. And that's basically what we want to find for the answer. But we also need to solve, like when we are solving one of these equations, we also have this t variable, which we also need to solve. So we have this single equation in 3D represents 3 equations in 1D. And you have basically 6 variables to solve. So you need at least 6 equations. If you do this also for the second hailstone, you already have like 6 equations. But you have these variables t, and actually this would be like the t that these 2 t's are independent from each other, because this is the t that intercepts where the rock intercepts the first line, and this would be the t where the rock intersects the second line, or the second hailstone. So we could separate these 2 things, call it t1, t2. These are also variables here. But once you add a second variable here, like the rock position and the rock velocity stays the same. So those 6 variables stay the same, and you have added 3 new equations. So long story short, if you add 4 hailstones to this, you already have, this is, well, I'm basically putting all of the numbers here. These are 4 equations, but they are in 3D, so they are actually 12 equations. And how many variables we have here? Well, 3 for the rock position plus 3 for the rock velocity, that is 6, plus 4 variables for these different t, the different times. So that is 6 plus 4, that is 10 variables and 12 equations. So if the equations are not like copies of each other, they are not like, how did you call it? If they are like linearly independent, or yeah, although these things are not linear equations because you are multiplying some of these variables together, but if they are independent enough, they will give you the solutions. And that's basically what I generated. I went to the Rust solution, ignore everything here, like on the top, this is for part 1. And basically I iterated over the hailstones, got the first 4 of them, and I'm zipping with these T, U, V, W names, just to have different variable names for these time variables. Oh, the formatter is messing up with the spacing. And then I'm extracting all of the hailstones and basically making up this very condensed, maybe a bit ugly, but yeah, I want to just show you before formatting this thing, like this thing will just generate a long, like a sequence of equations separated by commas. And basically I can ask some equation solver to solve this. And my first guess was to pass this thing to Mathematica, to Wolfram Alpha, which I have already done here, but I want to show you what happens. If I pass, I'm actually not sure if this will be right. Takes some time to compute. Oh, okay. Yeah, the problem here is that the syntax for this is using like times -1, and Wolfram gets confused by this ugly syntax. What we can do is change, I think if I message this a little bit, I can say instead of here the different variables, well, t is the name of this TUV time variable, and x, y, z, and vy, vx, vy, vz are the position and velocity of the hailstones themselves. Maybe not the best variable names, but let's roll with this. Let's turn this around. This will be hard-coded numbers, and I will put a space here, which is a bit weird, but you will see why. Basically, this makes the negative numbers be like, say, negative number times t, and if I join this negative with the plus, Wolfram treats this as plus minus, like the plus minus sign instead of plus a negative number. So, but if I add a space there, I think that will make it happy, and we can submit that. Like, this is a system of equations, just 12 equations, and you can see that Wolfram is powerful enough to solve this system, and here are the solutions. A equal 24, B equal 13, and C equal 10, and A, B, C are in these equations. Let's close this. These equations are basically what the initial position for the rock are in the three coordinates, like x, y, z is A, B, C. 24, 13, and 10, and you can see that this is the solution that we were looking for for the sample, and then the velocity is -3, 1, and 2, which are the next numbers here, -3, 1, and 2. And then T, U, V, W, those are the times. These are actually the times that the rock will intercept the different hailstones. So okay, like when I saw this, like, oh, nice, I got this. So let's just plug in, instead of running this with a sample, let's just plug in the actual input numbers. And the input numbers are much longer. But I say, okay, let's just submit this thing to Wolfram, and you can probably already guess what will happen, or not. Oops, you exceeded the maximum number of characters. So Wolfram has a limitation on the size of the query you can submit, and I was so frustrated by this, like, stupid restriction. And I think there is no way to like simplify these numbers, because they are like very big numbers. I have no idea if the creator of Advent of Code did this. I doubt it that he did this on purpose, so you cannot use some of these online solvers. And every other online solver for equations that I've tried was worse than Wolfram Alpha. Like some of them have like better UIs for defining things mathematically, but they all choked on 12 equations. So it was a pity. And I was about to give up, but a friend of mine recommended to use this Colab thing on GitHub. So I didn't know about this thing, and it's amazing. And also I didn't know about SymPy, which is like a symbolic algebra package that lets you basically solve this kind of equations directly. Maybe I can zoom in the font size a little bit here. So this is basically what I ended up doing. I printed these equations in a different way and pasted it here, and make this thing compute the answer. You can tell it to compute, and it just gets the answer. And then I just added these 3 coordinates, and this is how I got the solution. So that was the show. And then also, of course, I tried to search for a Rust solution. Not a Rust solution, a Rust package to use SymPy or some algebraic package for Rust, but I think nothing exists that is as powerful as SymPy, which is a pity, because I would love to do this directly in Rust. But yeah, let's close some of my previous tabs. This was for part 1, line intersection, that I was looking for. I also looked for this problem of finding the intersection of 3 given lines, a line intersecting 3 given lines in 3D, and I was reading like Math Overflow for some of this. There is a crazy solution here that talks about like this. I think this is kind of probably sort of like the expansion of the thing that I was trying to do by pen and paper, but it's such a mess. And there is even a YouTube video here of someone that solves this problem, and you can see that these are like volumetric things, like when you're talking about a line that intersects other lines. It makes a lot of like weird shapes, and it's quite interesting. I didn't watch the whole video, and like I think I have no chance of replicating this well, in the given time that I want to give this problem. So I will be fine with this SymPy solution. I just want to maybe refactor it a little bit, and yeah, I think I can write probably a notebook that just does this, just refactor this into a better shape and add the notebook to my repo here. So that's, I think, what I will do. Because another possibility would be to like just add the Python code to my repo, but that will involve having to configure and use Python, And I just don't want to get into that because that's kind of the ugly side of Python. Like the nice side of Python is that it allows you to do these things, which is the reason why everyone uses Python for like scientific things or computation things. But dealing with environments in Python and installing packages and things like that is like the worst thing about Python, or that's maybe my recollection. Maybe it's a bit outdated because I haven't used Python in many years. I worked maybe on 2014, 15, like 10 years ago or something. I have a brief job using Python. So my knowledge is very outdated. So yeah, I think the first thing that I want to do is maybe use some better variable names for this. And I will print, instead of printing everything joined by comma, I will just print every equation. So for equation in x, let's just print the equation. And the equations themselves, I would like to write them, instead of saying A, B, C, let's say, rock X, rock Y, and rock Z, because we can use, I was using single variable names in these equations because Wolfram Alpha and all the other like solvers for numerical equations, they expect you to use single variable names, but this is Python what we are going to put this into, so we can use actually like better names, I guess, or slightly better names. It's not like Rx is much better, but it's a tiny bit better, and also we can have some spacing for the math and have things be a bit nicer. So this would be the velocity that we want to find, like the velocity for the rock. I just call it Vx, Vy, and Vz. Then the different time variables, I probably call it like T1. Okay, you can be a string, I guess. T1, T2, T3, and T4, just to be consistent. And that's it, I think. Let's just generate these equations. Okay, what do I want to have actually in the notebook? Let's think about that first. I just call it T. If I put this, if I put this in the notebook, it will still be working, but it's basically the same thing that we have now. So okay, what do I want to put in the notebook? Like, I don't want to hard code these things. I want to show like how to get from the hailstones velocities and positions to the solution. And here I have the sample modified because I was taking out one of the hailstones. I actually don't know if this will work for using this hailstone, because this one is parallel to this one. So I don't know if using this approach when you have some hailstones that are parallel will work. But we will see. I want to, let's think. Let's have something like our hailstones. Actually, can we add like another code thingy? Can this be moved around? Oh yeah, awesome. Let's say sample hailstones. I want to have something that is more or less general. My cat is calling to something. Let's just modify this to be Python syntax. And we're going to just have two tuples. I think this supports also multi-cursor, which is awesome. Okay, and it's also like colorizing this. I'm not a fan of this like rainbow colorization of the of parentheses, but well, then let's leave it like this. Okay, so we are going to have this. Let's how do we create the these equations? Basically, by the way, these equations, as you can see, it's like they are not equations. Like they are not saying like equals. This thing should be equal to this thing, but these are basically equations that are equal to 0. So you move everything from one side to the other to leave like an equation equaling 0. So this is how we wrote this here. How do we want to make this solve here? Basically, I want to. I don't know if I want to like hard code everything. Oh no, not hard code. Like I don't mean hard coding everything like as the numbers, but maybe I could get like the first 4 hailstones. I say H1, H2, H3, H4, and then ignore the rest. I'm gonna say sample hailstones, and then we can just, instead of having these, we can have like H1 and then access. Each hailstone has the position and velocity also. Okay. Let's see how this would look. I think it will look horrible. So we'll have variables called h1 for the position and hv1 for the velocity, let's say. I don't think this is going to be very nice. Oh, by the way, did I execute this? Okay, that is executed. So this variable should now be valid. Okay, I don't know if Python actually allows to unpack like this. HV1, maybe it does. H2, HV2, H3, HV3. So H is basically the position and HV is the velocity. I could call it HP for hailstone position, but oh well. HV4. So here I got confused. This should be HV1. And then let's see. Let's grab these 3 and say these are the 2, 3, and 4. Same thing over here. I think this is not very pretty. And then we're going to have 0, 1, and 2 because we are accessing this thing, and we can do also more mass replacement here. Look at that multi-cursor editing. Okay. That is like 0, 1, and 2 are basically the x, y, and z of each of these 3 coordinates vectors, and then ABC and all of this I think should still be the same. So if I actually execute this, no, index error. Oof. line 9. Oh, I'm accessing a 3. How did... Oh, I'm an idiot. These 3 should be 2s. Should be 2s. Then h3 is messing me up. And also I got confused here. I got a lot of stupid errors. Okay, but if I run this now, oh, look at that. That is the solution for the sample, 24, 13, and 10. So this is working. It is quite difficult maybe to read what we are doing, so I think I want to maybe abstract this a tiny bit. I forgot about something, which is like the how was this slicing syntax in Python? Maybe 0. Like if I want the first 4, is this what I want? Yeah, great. I can ignore the 5th. And it turns out that also for the sample, even if here there is one that these 2 are parallel hailstones, this approach still works. And it makes sense that it works, because imagine that if you have even like 4 super parallel hailstones, and they are all in the same plane, like, and they are parallel, but if they start a different, like, we know that there is a solution that crosses over all of them, and so they have to be at a different points at a different time, and our rock has to intercept them all. So I think even with 4 parallel hailstones, you will still get a solution for this thing. So I think this is a very good way, and probably the way that the author of this, the author of Advent of Code, intended this to be done. So okay, let's accumulate the equations. We're gonna say equations. It's gonna start as an empty. Probably I could use a list comprehension or something like that, but let's see. We are going to say, instead of like this, we're going to say for each hailstone position and hailstone velocity in hailstones, sample hailstones, we are going to push some things into, I don't know why it's using two space for indentation. I think the standard in Python is 4. But we can also even like distract this, so let's call it hailstone X, hailstone Y, and hailstone Z. I don't remember if this is possible to distract like this in Python, but we will see. Hailstone velocity X, hailstone velocity Y, and hailstone velocity Z. So we unpack everything, and we're just going to say EQs. We are going to append 3 new equations in here. And the equations are going to be basically something like this. Oh, and the t variables. The t variables. Can we zip in Python? Python zip. I think it's at top. I just fell into W3 schools, but yeah, zip is a top level function. So we're gonna zip this, and we have the time variables here. So these 3 things. So okay, we're going to get this and this. I don't know if I can distract her like this. We will see. we will see. Actually, can we print this maybe? HX, let's print HX and just T to see. Value error. Not enough values to unpack. Expected 3, got 2. Okay, so I guess I'm getting first the tuple that represents the hailstone and then the T variable. Yeah, okay. This seems to work. Awesome. Let's do what we were trying to do, which is to add to the equations. We're going to add 3 new equations of this shape. So we're going to do A times T, and well, okay, we can use maybe the better names that we were thinking for these things. Like instead of ABC up to here, let's call it Rx, like the rock X, the rock Y, and rock Z, and then Vx for the rock velocity, Vy, Vz. And actually for the time variables, we can say T1. I think it's better to just call this T1, T2, T3, T4, so that it's a little bit more understandable what they are. T1, T2, T3, T4. Okay, and then we're going to say, okay, Rx plus T plus Vx for the rock minus the hailstone X minus T times hailstone velocity in X. And basically all of this equals 0. And we're going to repeat. I don't know how to repeat a line in this editor, so let's copy paste. And this is basically going to be the same. Can I? Yeah, I can use this and say Y and then Z. Right? And I think that those are the 3 equations that we want to add for this hailstone. And then we're just going to do call this solve function. So we can uncomment this thing. We can solve all of these equations, and the variables will actually be these things. I said save, but does this still work? No, we got cannot import Rx. Ooh. So is this only expecting single variable names? Is that what? Huh. Weird. SymPy import from SymPy ABC names with more than 1 letter. Can we have multiple letter symbols in SymPy? Okay. You can also import symbols and do this. This model does not define symbol names on demand. Import foo will be reported as an error because ABC does not contain the name foo. To get a symbol name foo, you still need to use. Okay. Okay, so we can use these symbols function to get our symbols thing. So let's yank this from here. Let's import solve and symbols, and let's have all of these be symbols like this. Okay, so we got this working, and that's great. That's great. We get the solution here. So okay, let's then, I want to do this for the sample hailstones and for the actual hailstones. So we are going to put this on a function. Let's call it find rock position, because that's what we want to find. That's what we care about, basically. And we're going to receive hailstones in here. We're going to do all of this inside of this function. Here we are not going to use the sample hailstones, we are going to use the real hailstones. This is a bit ugly how it goes over 80 characters, but it's fine. I wonder if like you can give a description to these symbols, like this is the rock position, but yeah, whatever. You can then use this is cool. Alright, so I wonder can we do something maybe like this time? No, let's keep it as this first, and then we can refactor. So we have this find rock position, and then let's execute this. Actually, this is not going to just return the solution. It should return the solution Rx. Let's call this thing just S for solution. SRY and SRZ. We execute this, and let's add another code snippet. I don't want to do things with AI. Find rock position. We can call this with a sample hailstones. And why didn't, oh, because Python is explicit about returning things. So we can, yeah. Okay, so we have that, and we can then do the sum of this thing, I guess, just to show the different steps on this. Great. And we can have the sample hailstones and the input hailstones, which we're going to do in a similar way. And we are not going to copy all of them for sure. Let's go actually the sample. Let's discard these changes. And the actual input, we are going to use only the first 4. So this is going to be a 2-nested tuple up to here and up to here. I missed the commas. Okay. All right, and input hailstones, awesome. We can execute that, and just add another code sample. Where is the thing to add more? Here. Okay, I want to do something similar to this, but find the rock positions of the input hailstones. And these are the actual positions, awesome. And then just do the sum of these things, which is the actual answer to this puzzle. No, not the sample, but the inputs. Okay, and that is basically the answer. Now I think it does look a little bit nicer. I would even like write some prose about this thing. And close the other things. Wolfram, you weren't very useful for this. Well, actually, no, it was useful because I got a confirmation that this approach was working using Wolfram Alpha, and then I just needed to like bypass that restriction of the maximum query size. But okay, what else? I was thinking about, by the way, is there a way to like run all the code snippets when something changes? Cross output communication, what? I don't know what's these things. Copying to cell, add a comment. So I don't know much about Python notebooks, but they seem very powerful and nice. So what I was thinking of doing is, let's say time vars, just use another set of variables for this, and something like that. Does that make sense? But we need to like rerun everything. That's to see if this works. But yeah, it seems it does. Oh, you can do a run all? Awesome, that's great. That's great. Yeah, I think this looks all right. I would like to maybe do some explanation, but I think I will leave that for like outside of this video, because I'm noticing I'm a bit, and it's already super late at night, so I'm a bit fussy already. Maybe the thing that I want to do is kind of add comments about like this thing, and say like the real input contains many more hailstones, but 4 are enough for this solution, enough to find the answer. And is this that like yeah, I guess this is some kind of like markdown or something like this, which is really nice. And like I would add also like an explanation of what we are doing here. like a single keystone line. The line that's a keystone travels through can be expressed as, and do we have some like math syntax for this? Maybe we do. V times V. I don't know if the math syntax. Oh, look at that! It does work. Cool. Cool. So I think I will add some like nice comments about what we like explanation of what we are doing here, but I will do that off camera. Maybe tomorrow or something. But yeah, this was what I wanted to do for this day, and I think this I can export also. Like yeah, I can save the notebook as saved successfully. But where did it save? Ah, no, you have to say download. Yeah, and you can download an IPython notebook file for this. And I think you can just put that on GitHub, and GitHub also displays the notebooks like nicely. So I think I will have that on my repo to like explain how the hell did I solve part 2 of this puzzle. But yeah, I think that will be it. I don't know if this video really warrants a thumbnail, but let's do it just for, you know, tradition's sake. And I guess this time I will have a nice notebook on the side. We can show some of this mess. What did we do today? Well, it was, oops, I deleted more than I wanted there. Still day 24, and I think what I thought when doing this using Python is, this is why people use Python on science. So this is why scientists use Python. Let's see how this looks. Yeah, it's not so bad. Maybe add some proper capitalization, because this is like a title. All right, this is good enough for me. Let's clear this better and run this like this. Okay, I think that this will be it for today's video. I'm already quite tired, so as usual, if you have been, thanks for watching, and see you later. Goodbye.